Okay, let's unpack this. Have you ever felt like science, for all its incredible breakthroughs, sometimes moves at a frustratingly slow pace?
Hmm.
Or you hear about a study only for it to be debunked later. It can feel like there's a disconnect, right?
Yeah.
Like the very engine of discovery isn't running as smoothly as it could.
You've really hit on a critical point there.
Cool.
The foundational processes of empirical science are indeed under significant strain. I mean, really unprecedented strain in the 21st century.
Right.
We're definitely at a crossroads where the sheer volume and complexity of information are challenging our traditional methods.
Absolutely. And that's exactly what we're diving into today. There's this widely acknowledged crisis in how scientific knowledge is generated and validated.
Yes, the validation part is key.
We're talking about a struggle with reproducibility, researchers kind of stuck in their own disciplinary silos,
Fragmentation.
and validation cycles that just feel incredibly slow. Think about this statistic, it's kind of eye-opening.
Yeah.
Across diverse fields, only maybe 25 to 40% of published findings are genuinely replicable.
It's a shocking number.
It is. That's a huge drain on resources and a serious impediment to real progress, isn't it?
It absolutely is. And our deep dive today focuses on a truly ambitious response to this challenge. Dynamic validation ecosystems, or DVE.
DVE,
Yeah,
yeah.
a concept proposed by Mr. Shahryar Ghiasi. And look, this isn't just an incremental improvement. It's presented as a radical reevaluation and re-engineering of our epistemic architecture.
Epistemic architecture. Wow.
Right. It's designed to create a self-correcting scientific framework that fundamentally redefines knowledge integrity.
That's a big promise, a self-correcting science. So how does it aim to do that?
Well, that's what we'll get into.
We're going to explore DVE's 4 core innovations that make this ambitious vision hopefully a reality, transforming science into something truly adaptive and resilient.
Exactly. 4 key pillars.
So let's really dig into the heart of this problem first. When we talk about the reproducibility crisis, it's more than just an academic concern, right?
Oh, definitely.
Imagine trying to build a new city, but only a quarter of your fundamental engineering blueprints actually work as expected when you try to use them.
That's a great analogy.
That's kind of the scale of the challenge we face in science. That 2015 Open Science Collaboration study putting replicability as low as 25%.
Yeah, it sends shockwaves.
Yeah.
And it really erodes public trust, which is crucial. Plus, frankly, it wastes immense research budgets.
Huge amounts.
And the issues run deeper than just reproducibility. We also grapple with what we call disciplinary fragmentation.
Right. The silos.
Exactly. Scientific fields often operate in their own separate worlds, each with its unique language, methods, assumptions.
Making it hard to connect the dots.
Incredibly hard, especially for complex global problems like, climate change or developing a new pandemic vaccine. These things inherently require insights from multiple areas simultaneously.
You can't solve them in isolation.
No way. Then there's the sheer inefficiency of our current validation processes, particularly peer review.
Peer review. Necessary, but
But incredibly slow.
yeah.
Publans reported back in 2022 that the median time for a paper to go through validation is around 14.7 months.
Over a year.
Over a year.
Yeah.
That's a significant bottleneck. And beneath all this, you often see these unvalidated assumptions lurking in models.
Like,
Well, think of certain econometric models where a core assumption, maybe like parallel trends and difference, might not actually hold. That can lead to skewed results.
okay.
Plus, we can't forget human cognitive biases. Nobel laureate Daniel Kahneman and his colleagues have documented these extensively. They can subtly influence research right from its inception.
So what does this all mean for us? It really sounds like we don't just need better lab equipment or more data. We need a completely new philosophy, a new way of thinking about how we do science.
Precisely. And DVE aims to directly address these systemic flaws by redefining knowledge integrity. It's not seen as a static endpoint, but a dynamic state.
Dynamic.
Okay. Achieved through multiple interdependent processes. And this brings us to DVE's 4 foundational pillars, each designed to make science more robust, more adaptive.
Okay, let's talk about the first pillar, because this is where DVE really starts to sound like something from, I don't know, a futuristic lab. Quantum sandboxing. What exactly is that?
Right. It sounds sci-fi, doesn't it?
Yeah.
But it's a method for rigorously stress-testing hypotheses before they even touch a real-world lab.
Before the lab. How?
Yeah, it starts with advanced AI hypothesis generators. Now, these aren't just like brainstorming tools. They're leveraging sophisticated machine learning to explore immense possibility spaces. The source mentioned generating over 1 million novel material designs, for instance.
1 million designs just generated.
Just generated. But the real power comes in the next step. These hypotheses are then fed into what are called multiverse simulations.
Multiverse simulations. Okay, you're losing me slightly.
Stick with me. Think of these simulations as highly detailed digital environments, almost like infinite virtual labs, where the AI runs countless permutations of experiments on these hypotheses.
Okay, virtual labs.
But what makes them unique is the use of physics-informed neural networks, or PNNs.
Pinidims.
Yes. This means the simulations aren't just random digital worlds. They have fundamental physical laws embedded directly into their code.
Ah, so they obey physics.
Exactly. It's like creating a virtual universe where the rules of physics are always enforced. And crucially, to go beyond mere correlation, DVE employs causal AI engines.
Causal AI.
Right. Some use specific algorithms like neuters, for example.
Yeah.
These are designed to uncover robust cause and effect relationships within these simulations, not just if A happens, B happens, but A causes B.
That's a big difference.
Huge. So the whole thing acts as a super advanced digital gauntlet, a kind of falsification sieve that only lets the most robust, causally sound ideas pass through.
Wow, so instead of spending months or even years on real-world experiments that might just fail, DVE can rapidly filter out the weaker hypotheses right from the get-go. That's an incredible efficiency leap.
It potentially changes the economics of experimentation completely.
Okay, so once a hypothesis has proven its mettle in this multiverse, survived the sieve, it's time for real-world validation. But DVE doesn't just stop at a single test, does it? It does 3 distinct phases.
That's the next pillar. Tiered reality anchoring. It's a 3-stage empirical validation process, scaling up the reality checks.
3 stages. Okay, what are they?
First, we have lab-scale validation. This is initial testing in highly controlled environments, but it's, let's say, supercharged.
So supercharged labs.
With technologies like robotic synthesis for rapid prototyping, think robots building and testing materials very quickly, and also digital twin technology.
Digital twins, I've heard of those, like a virtual copy.
Exactly. A virtual replica of the physical experiment or system that's monitored and analyzed in real time. It allows for incredibly precise replication and immediate feedback.
Got it. Stage 1, supercharged lab. What's next?
Next, if a finding holds up there, it moves to mesoscale validation. Meso meaning middle scale.
Okay.
This means scaling up the findings using vast federated IoT sensor networks.
IoT, Internet of Things, like smart devices.
Precisely. We're talking about networks potentially comprising over 1 billion connected devices, globally sensors everywhere, collecting real-world data across incredibly diverse environments. This provides a huge, distributed, real-time validation data set.
Wow, okay. From the lab to potentially billions of sensors. And the third stage?
The final stage is macroscale validation. Here, the validated findings are integrated into large-scale, complex, predictive models.
Like climate models.
Exactly, like satellite-integrated climate models or maybe sophisticated economic models. The goal is to assess their real-world predictive accuracy and their systemic impact at the broadest possible level.
So you see if it actually predicts things correctly on a big scale.
You got it. And throughout these tiers, DVE assigns a quantifiable measure called the Reality Anchoring Score, or RAS score.
Array score, like
Wow.
a confidence score.
Sort of, yeah.
Yeah.
It adapts to different research domains, dynamically weighing factors like reproducibility in the lab, correlation with the sensor data, predictive accuracy in the big models, giving a comprehensive confidence metric.
What's really fascinating here is how DVE creates this seamless thread, doesn't it? From the tiniest lab experiment through these massive sensor networks right up to global models. It's like building confidence brick by brick, really cementing whether something holds true in the real world.
It aims for a much more robust form of validation than just a single study or replication attempt, micro to macro.
Okay, now this next pillar, this really gets to the core of DVE's self-correcting nature you mentioned earlier.
Oh.
It's about building knowledge that actually gets stronger when challenged, not weaker. That sounds, well, counterintuitive, doesn't it?
It does initially. It's a concept called anti-fragile knowledge webs.
Anti-fragile, like unbreakable.
More than unbreakable. Imagine a vast, interconnected network. Every research claim is a node, a point in the network. And these nodes are linked by edges representing causal relationships. This finding supports that one, this one contradicts that one. Each node has dynamic stability metrics based on its validation scores, its RAS score.
Right.
Crucially, this network is described as a complex, adaptive system maintained by AI multi-agent systems. These AI agents continuously assess and refine the connections, the edges between the nodes.
So AI manages the web of knowledge.
In a sense, yes.
Yeah.
And this draws directly from Nassim Nicholas Taleb's work on anti-fragility.
Ah, Taleb, Black Swan guy.
That's him. He introduced the idea back in 2012. An anti-fragile system isn't just robust, meaning it resists shocks. It actually gains strength and capability from disorder, volatility, or stress. It likes challenges.
Gains strength from stress. Okay, how does that work here?
So, when contradictions or disconfirming evidence emerge within this knowledge web, a new study challenges an old finding, for instance, it doesn't break down. Instead, an anti-fragile response is triggered.
What does that look like?
The network dynamically adjusts the weight or strength of its connections based on the quality of the new evidence, the consensus among the AI agents managing the web, and even specific metrics designed to mitigate known human cognitive biases.
It factors in bias.
It tries to. The idea is that the entire knowledge system strengthens and refines itself in response to challenges. It becomes more robust and reliable with every new piece of information, even if that information is contradictory at first.
So wait, instead of an error or a contradiction making the whole system vulnerable or being dismissed,
Right.
DVE actually uses those errors or contradictions as a way to learn and get better. That seems like a fundamental shift in how we view wrong results.
It is. The goal isn't just accumulating facts, but building a resilient, self-improving structure of understanding.
Could it ever risk incorporating bad information, though, if the disconfirming evidence itself is flawed or maybe even intentionally misleading?
That's an excellent question, and it's why the system is designed to continually evaluate evidence quality and those bias metrics. It's not about blindly absorbing all data.
Okay.
It's about discerning what genuinely improves the web's stability and predictive power, dynamically adjusting its beliefs based on the most robust, trustworthy information available. It's a constant, evidence-driven refinement process.
That makes sense. It needs that quality control. Okay, fourth pillar. One of the biggest frustrations in science, I think we can agree, is how often different fields just don't talk to each other.
Oh, absolutely. The silos again.
Even when their problems are clearly related, DVB seems to have a really innovative, maybe even radical solution for this.
It does, and it's called cross-paradigm translation engines, or CPT engines.
Cross-paradigm translation, breaking down the walls between fields.
That's the idea. These are described as highly advanced AI agents, built on foundations similar to large language models we hear about today, but with a significant enhancement.
What's the enhancement?
They incorporate something called brain-computer interface-derived cognitive patterns, a sort of neurocognitive fusion.
Whoa, hang on. Brain-computer interfaces, like reading brain activity.
Essentially, yes. The concept is that these systems can incorporate unique value vectors derived from BCI data. This data, as explored in some future-facing research mentioned in the source,
Right.
captures subtle human neurocognitive patterns associated with insight, analogy, and creative problem-solving. How humans make those leaps.
So the AI learns how humans connect disparate ideas, not just what ideas are connected.
That seems to be the core idea. It allows the CPT engines to detect deeper, often non-obvious, isomorphic relationships, similarities in underlying structure or function between concepts that might exist in vastly different scientific fields.
It's like finding a connection between, I don't know, galaxy formation and protein folding.
Potentially, yes. Things that look completely unrelated on the surface might share underlying mathematical or structural principles. And to speed up this search through incredibly complex data landscapes, the source mentions they even employ quantum annealing.
Quantum annealing for finding connections faster.
Right, it's a type of quantum computing that's good at optimization problems, like finding the best connections or analogies hidden in massive amounts of information, much faster than traditional computers could.
This raises an important question. So DVE literally uses insights potentially derived from human brain activity to help AI find connections that we might never have consciously seen between, say, seemingly unrelated fields like material science and economics or biology and cosmology. That's quite a leap for interdisciplinary research.
It really is. It's about leveraging that unique human spark of abstract analogy and insight, and then scaling that ability exponentially through advanced AI and potentially quantum computing. The aim is to bridge those traditional silos not just by encouraging collaboration, but computationally.
Fascinating. Okay, this all sounds incredibly impressive in theory, groundbreaking even. But the proof, as they say, is in the pudding. does it actually work?
Well, the source material presents results from testing DVE on some truly daunting grand challenges.
Like what?
Things like the search for room temperature superconductors, finding new interventions for protein folding disorders, which are linked to diseases like Alzheimer's, and predicting climate tipping points. Big, complex problems.
Definitely grand challenges. So what did the numbers show when compared to, say, conventional science?
The performance metrics reported are, well, genuinely remarkable. Let's break them down. First, reproducibility rate.
Okay, the big one we started with.
Exactly. DDE reportedly achieved an exceptional 97.3% reproducibility.
97%. Compared to...
Compared to the conventional baseline mentioned earlier, around 38.7%.
Wow.
It's not just a slight improvement, it's a 151% increase. The source attributes this largely to those rigorous multiverse falsification sieves weeding out weak hypotheses early.
Fewer dead ends, much higher confidence. Makes sense. What about speed?
Time to validation. This is where DVE appears truly transformative. The average time reported was a mere 18.2 hours.
Hours, not months.
Hours, compared to the conventional 14.3 months.
I'm doing the math. That's an astonishing 580-fold acceleration.
It is. Imagine, instead of waiting over a year for validation, potentially getting robust results in less than a day. It turns science into something much closer to a real-time feedback loop.
Mind-blowing. What else?
Cross-domain yield. This measures how many useful solutions bridging different fields were found per problem.
Okay.
DVE reportedly generated 6.2 such solutions per problem, while conventional methods averaged only 0.3.
6.2 versus 0.3, that's almost a 2,000% increase.
The numbers are dramatic. It suggests breakthroughs emerging from unexpected intersections, fostering a kind of intellectual cross-pollination that's currently very difficult to achieve.
Finding solutions we weren't even looking for in the right places.
Potentially. And finally, predictive accuracy in those macro-scale tests.
How well did it predict real-world outcomes?
It reportedly jumps from 62.9% for conventional approaches to 84.1% for DVE. That's a 33.7% improvement in accurately predicting large-scale phenomena.
And that's attributed to the reality anchoring.
Correct. The rigorous reality anchoring triangulation across the lab, meso, and macro scales, giving a much clearer picture of real-world impact and applicability.
It's hard to overstate how transformative these numbers are if they hold up. It means we could potentially see solutions to incredibly complex problems, not just faster, but with far greater reliability and maybe from completely unexpected angles.
It suggests a fundamental change in the nature and pace of scientific progress, moving perhaps from reactive problem solving to something more proactive, more like discovery engineering.
And with such powerful technology, such profound capabilities, you have to wonder about the ethical implications, right? Especially with things like BCI integration.
Absolutely. And the proponents claim DVE was designed with robust ethical safeguards built right into its core architecture.
Okay, like what? That's crucial.
Well, for instance, concerning neural data privacy, that BCI data we talked about.
Yes, the brain activity insights.
The proposal involves using homomorphic blockchain technology for encryption.
Homomorphic, meaning?
I mean, the data can be computed upon, analyzed, without ever being decrypted. Think of it like a secure, transparent vault, where calculations happen on the encrypted data itself, keeping the raw individual data private. The Neuroethics Consortium is cited as exploring this for 2028.
Okay, so privacy is baked in technologically. What about bias in the AI?
Good point. The system description includes continuous monitoring for algorithmic bias. It uses strict statistical thresholds. The source mentions a delta less than 0.05 on protected attributes to try and ensure that biases don't unfairly creep into hypothesis generation or the validation processes. Preserving fairness is a stated goal.
Constant vigilance against bias. And what about the knowledge web itself? Could it be manipulated?
That relates to anti-fragile resilience. The claim is that the knowledge web stability actually increased by 22.4%, even when subjected to deliberate adversarial contradiction injection.
So when someone tried to feed it bad info,
it apparently got stronger and more accurate, demonstrating an inherent ability to self-correct and withstand attempts to mislead it, rather than becoming brittle.
That's fascinating. It learns from attacks. It's incredibly reassuring, then, to hear that this isn't just about speed and power, but also about building in trust and responsibility from the ground up, especially when dealing with sensitive data and powerful AI.
It's presented as an integral part of the design, not an afterthought.
So how would something like DVE actually be put into practice? It's clearly not about replacing scientists, right? It sounds more like a new kind of partnership.
Exactly. The model described is one of symbiotic human-AI collaboration. It starts with research prioritization.
Focusing the power where it's needed most.
Right. Grand challenges, those complex, high-impact problems are identified and assigned a gap criticality score. Only those exceeding a certain threshold, say greater than 8.0, are prioritized for DVE's high-speed pipeline. It focuses resources.
Makes sense. And what do the humans do in this DVE world?
They play crucial redefined roles. There are hypothesis gardeners.
Gardeners, I like that.
Yeah. These are domain experts who guide and refine the AI hypothesis generators. They provide essential human intuition, contextual understanding, maybe steer the AI away from silly ideas, and crucially, provide ethical oversight.
So, tending the idea garden.
Pretty much.
Yeah.
Then there are validation curators. These are cross-disciplinary teams who audit the anti-fragile knowledge webs, ensuring the quality and integrity of the evolving knowledge structure, like librarians and fact-checkers for the web, and ethical governors, independent bodies, specifically overseeing the neural data integration, the bias monitoring, the overall ethical performance.
Independent oversight. Important.
Very. And resource optimization is also key. Allocating that immense exascale computing power based on a value triple constraint model, balancing potential impact, feasibility, ethical risk, and cost.
What's so interesting here is that image of cultivating knowledge, humans as the gardeners and ethical guides, making sure the AI is truly working for the greater good, tackling humanity's biggest challenges. It's a very intentional, guided ecosystem, not just raw computation.
That seems to be the vision. Human wisdom guiding artificial power.
This whole concept, though, it stretches beyond just optimizing science, doesn't it? It really makes you pause and consider some profound questions about what we understand as knowledge, truth, maybe even our perception of reality itself.
It absolutely does. The integration of brain-computer interfaces, for example, brings significant neuroethical considerations right to the forefront.
Like what specifically?
Well, there are discussions around neural firewalls, the need to protect individual cognitive identity, to prevent what some call identity erosion, a potential blurring of the lines between individual thought and the AI when cognition interfaces so directly. The Neuroethics Consortium is flagged as looking into this.
Protecting the self.
And then there are potential hyper-reality risks. If we can simulate multiverses with such incredible fidelity.
Right, those multiverse simulations.
There's a theoretical concern, echoing thinkers like Jean Baudrillard, that we might develop a preference for these highly curated, perhaps even perfected, artificial realities. A hyper-reality where the simulation becomes indistinguishable from or even preferred over the methy real world.
Losing touch with reality because the simulation is better, that's unsettling.
It highlights why robust governance, like the blockchain consent and differential privacy for neural data, is presented as absolutely non-negotiable.
Definitely. And what about knowledge itself? Epistemology.
From an epistemological standpoint, our theory of what knowledge is DVE seems to fundamentally reconfigure our understanding of truth.
How so?
Well, truth isn't presented as static anymore. In DVE, it's more about dynamic stability. A hypothesis is considered true or valid based on its persistence, its resilience across simulations, and its robust anchoring in diverse empirical realities over time. It's fluid, yet strong.
Truth as a process, not a fixed point.
Exactly. And the role of the human researcher shifts, as we discussed, from maybe a solitary explorer to more of a hypothesis gardener or curator within an AI-nurtured knowledge landscape. It implies a new era of really deep human-technology symbiosis. And DVE fosters this anti-fragile epistemology where contradictions aren't failures, but crucial opportunities for growth. As Donna Haraway might put it, errors don't just happen. They actively propagate corrective updates across the entire knowledge web, strengthening it.
This raises a really important question then. If our understanding of truth itself becomes something dynamic and evolving, constantly being refined and strengthened by new data, even by challenges and contradictions, how does that fundamentally change the way we approach big, complex problems in the future, especially those tangled up with deeply entrenched beliefs or conflicting worldviews?
That's perhaps one of the most profound implications to grapple with.
What we've explored today with dynamic validation ecosystems, it really isn't just presented as an upgrade to science. It feels like a fundamental shift, moving from a maybe linear, often fragmented process to an adaptive, self-optimizing ecosystem. It's like turning a traditional library into a living, interconnected, constantly learning brain.
And this paradigm shift, according to the proposal, is achieved through that powerful methodological pluralism, seamlessly integrating quantum simulation, digital twins, neurocognitive fusion, all these advanced tools,
Plus the validation.
plus continuous validation through that unique tiered reality anchoring system. And crucially, built on a foundation of robust ethical governance with embedded bias detection and neural privacy protocols.
All while strategically optimizing immense resources for the most pressing global challenges.
That's the package.
Imagine a future where science could genuinely keep pace with our fastest-moving global challenges, from climate change to, well, as the source material explicitly mentions, establishing highly reliable global pandemic prediction networks. The potential impact is staggering.
This framework really tries to establish science as a living, evolving system. Knowledge isn't merely discovered passively, it's actively cultivated, refined, strengthened with every challenge. It really makes me wonder
Yeah.
if our collective knowledge systems could become truly anti-fragile like this, continually learning and strengthening from every piece of new information, every stress test. What seemingly unsolvable problems, the ones that have stumped us for decades, could we finally conquer together?
That's a powerful thought, and maybe for you listening, what might it mean for your own learning, your own understanding of the world, if truth itself is seen as something always dynamically being refined, always under construction, definitely something to mull over until our next deep dive.